Well, first of all, thank you for the invitation. Sorry I couldn't be here tomorrow. I wanted to be here, but we were doing experiments, and tumors tend to grow in a very random way. So they happened to be mature at yesterday for the experiment, so I could not come. It failed miserably. We did 9 mice, none of them worked. So I just want to give you a message here. Most of the time, it doesn't work as well as what I'm going to show you. We don't say Eureka very often. We say mostly, oh shit. And I think that's the common theme. And so especially for students, don't be afraid of failing experiments. Happens quite often.
May I straightforwardly ask a question? What's the rate of Eureka to oh shoot?
Of what?
What's the rate?
I think it's maybe 1 to 100, maybe. I think it's about it. and then we get the echo from a single line. So every time we do a pulse echo with conventional focused ultrasound, we do one line. When we're doing plane wave imaging or ultrafast imaging, what we do is that we send we send an unfocused beam, and that unfocused beam will hit all the scatterers, and then we'll get back the signal, but we'll get back the signal from all the different transducers. We will not sum them in any way. And then from all that data, we will beamform that data and reconstruct a single image from a single pulse echo. So in one case, a single pulse echo gets you one line. In the other case, a single pulse echo gives you a full image. And the difference here is that in this case, you have 50 frames a second, which is already the fastest imaging system in the medical field currently. But if you go with these ultra-fast technique, you can go up to 6,000 frames per second. Even for mice, we can go even at 20,000 frames per second. So this was actually introduced by my colleagues quite some years before I arrived. And the first application was for shear wave imaging. And so the shear wave imaging, the basis of shear wave imaging is to send a pulse of shear wave, which is a mechanical wave that moves a lot slower than the compression wave that we are using for imaging. And by imaging this shear wave propagating, we can measure the velocity in each point, and that velocity can be converted into a map of the elasticity. And that map is currently exploited for example, for the diagnostic of breast cancer and liver disease. So another nice thing about ultrafast imaging, so this can only be attained if you're going fast enough. Another nice thing about ultrafast imaging is that it improves quite drastically your sensitivity to blood flow. So if you take, for example, this is a plane in the brain of a neonate. So you see how the images in milliseconds. So you see how fast it is going, and you see all this decorrelation that comes from blood flow. So now, if you convert that into a map of the vascular of your vascular structure, and here it's in the rat. Here we have a coronal plane in the rat. And you can see actually the whole vascular system inside the rat brain with a much higher sensitivity than what you would have with conventional focused ultrasound. And here you're so sensitive that what you see here is actually the modification in blood flow with respect to an epileptic seizure that is propagating inside the brain of the rat. And so that's because ultrafast imaging allowed us to increase Doppler sensitivity by a factor of about 50. So this is what has been done with ultrafast imaging currently. You can do a bunch of different things also, working with these contrast agents that I talked about. Yes?
I have a question about the
Yeah.
previous slide.
Yeah.
Is this real time or?
No, well, this is not real time because it needs a lot of data processing. Because the beamforming takes a lot of time. But it's long acquisitions. So currently we can do continuous acquisitions for even hours. So we can, for example, look at resting states inside the brain of rats, which goes with cycles which are very slow. So actually, what's interesting about ultrafast is that it gives you a much higher sensitivity to slow flow. So that's the irony of it. So when you're doing ultrafast, you can do many things with contrast agent. I'm not going to talk about any of them except for these two. And so it's the combination of these contrast agents that I talked about and the ultrafast that provides you interesting new applications. You can also do therapy with these kind of scanners. I'm not going to go into this, but you can use ultrasound sensitive agents that will evaporate under the effect of an ultrasound pulse and guide this to a patient. So one of the things that you can do with ultrafast imaging and contrast agent is, for example, try to do molecular imaging. So the concept of molecular imaging here in ultrasound is that you're taking your contrast agents, which are balls, you surround them with antibodies, for example, or other targeting moieties, and then you can inject them in the animal and try to see if they target inside a tumor. So this is an experiment that we've done a few years ago, and the question was, if we try to target the bubbles to a specific anti-tumor agent, can we actually make them tag specifically the tumor? And this is something that we were achieving with our imaging system. So in green, what you see is the specific signal from bubble, and in gray you have the conventional ultrasound image. And what you see here is the tumor. You see the tumor here also, but the difference here is that in one case you have bubbles that are not targeted, so they do not specifically tag to the tumor, but they actually accumulate inside the tumor. And so we've done this with these contrast agents, which were targeted, and with ultrafast imaging, and we came up, well, we found something interesting happening when we were doing this kind of images in the tumor. Is that when you're doing images with a very high frame rate, and you're doing a technique that, a bit like the previous talk, where you do differential imaging, you subtract one image from the next one. What you see from doing ultrafast imaging of this tumor filled with bubbles is all these blinking spots. Now that's interesting, and if you look at a few pictures, well, you see one spot there. You see one spot there, one spot there, one spot there, one spot there, and they only arise when you inject bubbles in the tumor. And actually, I hope it reminds you from this. So I hope you can make the link between this technique where you have blinking agents on the structure of the cell, and our blinking agents, which are in the vessels.
This is ultrasound?
No, this is optics.
Okay.
This is optics. This is Bidzig. Well, this is actually from Bidzig talk that he gave after his Nobel Prize.
Go to the subcell resolution.
So in this case, you get from a few hundred nanometer in resolution in optics to a few nanometer to a few tens of nanometer. So you get a factor of 10 to 100 in resolution, and what we hope for is that we get the equivalent gain in ultrasound. So, but what I wanted to show you is the analogy between the two. In one case, you have ultra-fast images with a contrast agent that blinks, and we have also a contrast agent that blinks under ultra-fast imaging. So we left the tumor field, and we started to go back to the in vitro, where there's a lot less chance that it will fail. So we made these little channels about 40 microns in width, and started injecting bubbles inside these vessels, and look at them with an ultrafast ultrasound scanner. And what we realized is that if you look at the image, the ultrasound image, which is a grayscale image, you'll see that the spot linked to the passage of the bubbles, the channel, is actually quite large with respect to the channel itself. But if you take the bubble and you look at the bubble in each of the image, and you find the center of each of the bubble, you can pinpoint their position within the channel with a much higher resolution than what you get actually from that from this presentation. So I understood from the talk this morning that we also have to give like advice about science and how to do science and methodology. So one advice that I have to give you is that don't present something when you're not ready to publish it. So we presented this, and we made a proceeding about it, and very rapidly other groups started picking up on this. So there's two other groups that started to look at this. A group in Toronto where they did pretty much the same thing, where they injected bubbles inside channels and tried to see if they could beat the resolution limit of ultrasound. And so what they were able to show is that if you send a very low dilution of bubble and you have a conventional imager, you don't have to go ultra fast. You can actually get a much higher resolution. And also the group in London applied this in vivo on the mouse ear. But the big difference between the technique I previously proposed and also the optical technique is that rather than relying on ultra-fast images, they rely on slow images, and the accumulation of very low concentration bubbles. So basically, the idea is you add a bubble at a time and you track it on your image. But there's a big difference between this and the technique that we propose, or the one from Bedzig, is that what we want to, in our case, what we want to see is have very high concentration of agents, and then try to decorrelate it through the ultrafast images. So there's a big difference in between the two, and we continued more or less on the ultrafast method. So first of all, what we try to do is, can we actually do that in 3D? And can we show in a vascular model that we have achieved a much higher resolution? So, my student Yann de Sailly injected bubbles inside a vascular system, a pseudo-vascular system made in a microphilic system, made in PDMS, and looked at it with an ultrasound piezoelectric matrix. And so we send plane wave, and we take very high frame rate images, and then we see bubbles passing by. And so if you take an optical image of these channels, well, obviously you can distinguish them. But if you're doing conventional ultrasound images, well, then it's impossible to distinguish them from each other. Why? Because in this case, you're actually limited by the wavelength of the ultrasound that you're using. But if you're taking each of the bubbles, taking the center and pinpointing them on the image, then you can reconstruct these images with a much higher resolution than what you could achieve with conventional ultrasound images. And just to give you an idea, the distance between each of these channels is less than the wavelength. So normally, in conventional imaging, you will not be able to separate them at all. So the first question that we asked was, well, if we can bypass the resolution limit in ultrasound, what's the actual limit of resolution that you can achieve? And a model that we created showed that you could actually link not the resolution to the wavelength anymore, but to the signal to noise ratio of your system. So better is your system, the better the resolution you will attain with that technique. And so what you end up having is that if you're taking, for example, an ultrasound frequency that we're using conventionally for breast imaging, we predict that we can attain a resolution of 10 micron, which is, well, in this case, this is an order of magnitude below the resolution that you would acquire, that you would have with this kind of frequencies. And in the rat brain, we realized that the model was predicting a maximum resolution of 5 micron. And this is deep. This is at 12 millimeter in depth. So this is the kind of resolution that you can acquire currently with optical technique, but with penetration that can get you the full brain. So that's something to us that was really interesting. So we saw that as a challenge, and our student Claudia Rico started work on how to image the brain with this technique. So how does it work? So we have an ultrasound transducer that is installed over the brain of the rat. In some case, the skull is thin, so a bit like the technique that you've seen before, but there's no trepanation; it's just thin. In the other case, we leave the skull just to give you a comparison. Then we send very high concentration of bubbles. So the question is not to have low concentration of bubbles. We send the highest concentration of bubbles that we can achieve, and then we start acquiring at high frame rate images inside the brain of the rat. So what I'm going to show you is mostly, well, it's all coronal plane images. So we put the array like this, and you see a cut like this through the skull of the rat. So when you do this, what happens? So this is the kind of image that you obtain when you take very large stacks of images inside the rat brain. And in this case, it's 70,000 images. And these 70,000 images then are filtered to remove the tissue. So obviously the bubbles with respect to the tissue are much less echogenic. So to extract the bubbles, you need to have specific filters, we use singular value decomposition to extract the bubble from the tissue. So what you can see here is that you can actually track the bubble one by one. And you can see them passing by, like you can see. You could follow this one, and then it goes up. So actually, knowing the anatomy of the brain, you can say, well, this was probably in the vein, and the one going down is probably an artery, because we know that arteries in the cortex are plunging and veins are coming up. So this is actually the hard part, how to get distinct bubbles, distinct from each other and distinct from tissue. After that, it's more or less gardening. So I'm going to show you how we do the gardening, but it's just gardening.
Why don't you do just harmonic imaging then? I mean, that would get rid of the tissue.
Well, actually, harmonic imaging doesn't work very well in our view. At 15 megahertz, you don't exploit the resonance of the bubble. It's very far from the resonance of the bubble. So with respect to these singular value decomposition filter, it's a lot less efficient. Actually, we're currently publishing a paper on the comparison between harmonic imaging or pulse inversion or amplitude modulation with respect to these kind of filters, and these kind of filters are systematically better. So even in presence of motion. So it's, yeah.
So you say you use as many bubbles as possible, but in the end you still have to have little enough bubbles in the brain that you can still differentiate the single bubbles. And that is just because the arteries and veins in the brain are small enough that there's only a handful of bubbles passing through.
Well, there's that, and the fact that you only have a slice of 200 micron in the case of, because we don't have this resolution in 3D because we only take a plane, and so the plane has a thickness, and that thickness is 200 micron. But then there's another also effect, is that when you're doing singular value decomposition, you're removing all the spatially coherent signal, spatially interpolate coherent signal. So actually, you will remove the bubbles that are too close on each other. And in vessels where there's a lot of bubbles, and you realize later that vessels where there's a lot of bubbles actually disappear because of these filters. So what is this gardening I was talking about? Well, it's very easy. You take your image. So this is the kind of image that we start from. This is the top of the cortex. We don't see anything. And then we do the singular value decomposition. We start seeing these sources. We interpolate the sources. We find the center, and then there you go. You can pinpoint the exact zone of your, the exact center of your bubble, because you know very well the point spread function of your system. So what happens when you do this? 1 second. Whoa. It's a large file. There you go. So if you track each of the bubbles, then you can reconstruct these vessels, because you know that the bubbles are purely vascular. So when the bubble is, when you can track a bubble, then you can say, well, that's a vessel, I know it, and then reconstruct the vessels one by one by the passage of multiple bubbles every time. So we acquire over 180 seconds, so that makes a total of 70,000 to 100,000 images in total. So you need that large stack of data for the filters to work well, and for the number of bubbles that you need to acquire to do these kind of images. So if we take the cortex, and we would do a conventional Doppler imaging with the kind of resolution that we obtain, this is what we will see. But if we do the technique, the ultrasound localization microscopy, then you would actually see all the fine structure of the vessel. You can see, for example, you can see 2 vessels that are closer from each other than, of 16 micron, knowing that the wavelength here is about 100 micron. And you can see vessels about 9 micron, but they actually could be smaller, but actually our resolution is limited to about that. And you can see much larger vessels very easily. Actually, these vessels, to us, we call them the large vessels, they're 50 to 60 microns in width. And so, since you can do these scans, well, you can do a scan over the whole brain of the rat in this case, And as you can see all the structure down. This is 12 millimeter below, and the resolution is about 8 micron down to the lowest part. Another nice thing about this is that when you interpolate the position of the bubble, then you have a very good resolution both in time and space. Because in time, actually, we have 2 milliseconds between each of the images. So you can actually do a very precise vector flow. So if you do the vector flow, then you pass from a bubble density map to a vector map, where you can see, for example, the bubble in the larger vessels, they're going faster, and then they slow down as they go down inside the cortex, and then when they split, they go slower and slower. And what you notice is that the dynamic range in velocity here is between a bit less than 1 millimeter to a few centimeter per second. So we actually can see a broad dynamic range of blood velocities. And the way we measured our resolution was actually through the blood flow itself. So if you take a vessel, for example, and you expect that you would have some sort of parabolic or Poisson flow, what we did is that we reconstructed the image with a different resolution, a smaller and smaller resolution, and then we were able to keep statistical significance between each of the points until we reached 8 microns in pixel radius. So to us, the resolution of this methodology is about 8 microns. So obviously you can do these maps since you have the bubble positions. So this is the nice thing also, is that you're not talking about images, you're talking about bubble position now. So you can do all these things with vectors, and you can do all these planes. Now I told you that we thin the skull in some cases. Well, all these cases were when the skull was thin. What happens when you keep the skull? Well, you're in a rat, you're at high frequency. What happens is that you get your signal quite attenuated by the skull. So now the skull is still on the image. That, by the way, that also tells you how good is the singular value decomposition filter for these kind of things, but the skull just disappears. And the skull is by far the most echogenic structure that you will find in these ultrasound images. But what we can notice from these images is that we lose a lot of signal to noise ratio, but in fact we keep a fairly good resolution. And here the resolution is still about 20 micron, even though we have the skull. But it's just that we lose a lot of the part of the bubbles that were where the signal was attenuated with time. So, just to give you a little summary, so by taking long stacks of ultrafast images, we're able to extract the bubbles from the images and find the centroid and find where they were going in the images, and to reconstruct these kind of images over the whole brain. The advantage of this is that it goes beyond the diffraction limit of ultrasound, and at a depth that's about, well, that covers the whole brain of the rat, in this case about 12 millimeter. Obviously we're limited by a few things. The time of acquisition, obviously. Motion correction will have to be implemented, but that's something that we're currently working on. And obviously it's a very, very large stack of data. We acquire easily 50 gigabytes of data every minute, so that's something that we have to process. So maybe it takes 3 minutes to acquire the data, but it takes a few hours to process it currently. But we hope that with Moore's law, eventually this will become shorter and shorter. On this note, I will stop here, and I would thank, well, obviously this was not done by myself only. And there's a large group at Institut Langevin, and I have to thank a few people like Claudia Rico, who did most of the work, Yann de Sailly, and Michael Tanter, who's heading the group there. So, thank you very much.
Do you need all your domains to have exactly the same size? Can I produce the variation?
Well, actually, they can vary as much as they want. In fact, the only thing that you want is the ball to be echogenic and moving. If it's stuck, it will not be picked on by the filter. But actually, if they're very different in size, actually it might help the filter in distinguishing a bubble from each other. Yes.
So how do you decide when to stop? I mean, you get some vessels after 10 seconds and you get more vessels after 30 seconds. You would probably get more vessels after 2 hours. Where's your...
No, it's more or less linear in fact. If the longer you acquire, the smaller the vessels that you get. So if we go to 10 minutes, we'll see even smaller structures. Currently we're saying maybe 8 microns vessel. What you can see on histology, you can go down to 5 microns. So theoretically, we could go down to 5 microns in vessel size and having even smaller branches. But there's a point where you have to stop the experiment.
Would it help to use smaller bubbles, or do you use too much signal then?
Well, yeah, there's a compromise there because the bubble has, since we're not using bubbles that are resonant, in fact here we just need bubbles that are very echogenic and big enough. If we use smaller bubbles, we will have less signal, and we will have the same problems that what you saw with the skull. Is lower SNR, less bubbles, you cannot reconstruct the whole of that. This is also something that we're trying to work on because obviously if you're using smaller bubbles, you can access not necessarily vessels, but structures outside of vessels that currently we cannot do with purely vascular bubbles.
Yes. I have a very naive question. What do you think about, instead of using bubbles to detect the vascularity, to use optics in terms of a spectroscopy, detection of oxygenation, hemoglobin, disoxygenation, vascularity? What is your opinion about that? Sorry.
You mean comparing optics and this technique? Well, basically, to me, they're complementary in the sense that we will probably never get to the same resolution as confocal microscope, for example. But that's to me that's impossible. But we can, in general, we will go deeper than optics, and we can also benefit from the fact that it's also a very common medical imaging system. So in my view, they're complementary. Optics will have much better resolution over superficial structure.
I am talking about optoacoustics.
Optoacoustics.
Yes. No, optoacoustics.
Well, you were talking about fluorescent structure, so it is doable with these kind of structures. We discussed that quite significantly with the immunohistochemistry. I mean, the same idea can be applied on any any imaging system where you can find these blinking sources. And blinking can be through motion or can be through another process like vaporization. So this is totally doable in my view.
Hello. Yes, very nice work. I have a question concerning the way you're processing your data. Because if I understand it correctly, you make a series of images, then you look at the contrast change or signal changes in time, and you use this as video composition.
Yeah.
And then at the end, I assume you get again value and get vectors, and then you reconstruct by selecting some of them. And this is potentially the reason why bubbles that are static are eliminated. Am I wrong?
Well, yeah, the bubbles that are static are eliminated because they're both spatially and they're both coherent in space and time.
So where do you put the limits? Because then the question is that do you have kind of threshold velocities? In other words, can you distinguish with your technique the rapid motion in arteries and the slow motion in veins, or saying that the bubbles are going that way and going back that way, that gives some directionality?
Well, the dynamic range that we could see was between a bit less than 1 millimeter per second to 15 to 20 millimeter per second. So within that range, within that slice, we were able to get that range. Obviously, that depends on the threshold of input, which is totally empirical currently, and that's something that you have to select yourself to determine how to separate the ball. It's actually, we can also help ourselves with the spatial correlation. because we know that we can extract, we can find the limit in the eigenvector by saying that everything that has a very high spatial correlation will be eliminated, and everything that looks like a point will be conserved. So we can play with these two parameters to find the right empirical limit. So that's what we do.
Two more questions behind? Just before there was somebody? No? No more questions? Yes?
How do you distinguish the movement which is connected with the breathing? So the image could move a little bit because the patient breathes, and the movement of bubbles connected with low velocity.
Well, right now we don't, in the sense that...
Is it possible to do it here?
I think, oh, for sure. So we don't, because we put air bars in the rat, so the rat is quite static. But we are currently working on motion correction. It works because when well, for example, when I show you elastography, it relies on very fine motion that you detect caused by the shear wave, and you can. That proves to you that you can find motion that are much smaller than wavelength every point on your image. And since we have this very large stack of data, before we use these filters, we can actually find the motion of the entire image at every moment with a very high resolution, with a much with a resolution much smaller than wavelength. So we can correct each image from each other. And then every time we find a bubble, we recorrect their position with respect to that motion that we corrected. And so this is something that actually it works. There's some, I decided to show it here, but there's some mice that did, well, there was a problem with the ear bar, and they did have a lot of motion and were successful in correcting that motion with these kind of algorithms.
Yeah.
So, why a rat's brain? I mean, who is interested in the activity of a rat's brain? I mean, yeah, the contrast agents, they are clinically used every day, and the plane wave imaging that you do that is very low mechanical index, so it's safe.
Yeah.
So why not to try it immediately on human vessels? That's the first question.
Yeah.
And the second one, you are looking at see the microbubbles which are in a kind of confined space. So that's why you can see something. And if you would try to look at the blood streaming inside the heart, for example, you wouldn't probably see anything.
Well,
have you tried on any other?
This is also something we're working on. One of the issue here, well, first I'm going to tell you a story. It's, how much time do I have?
Yeah, 5 minutes.
So again, that's a scientific lesson, I guess. So this is pure luck. Huh? This is pure luck. Okay, so my student was working on another project when she came up with this. In fact, we were working with another student on super resolution, but we were purely in vitro. We were doing these channels and whatever I showed you. But she was trying to look at functional imaging inside the brain. And so how to go through the skull and try to look at the activity of the brain without removing the skull. And so we were adding bubbles. And so this is why we're doing the brain. And then when I looked at the data and I applied a filter, then we found these single events, and then we connected the dots, and then we ended up with these kind of images. So that's why the brain. It's also very nice because it's over a single plane. So a coronal plane is very nice in this case. It doesn't move, so it's also very nice. And to answer your question about the heart, here is the biggest vessel in that slice. You don't see it. That's because of the filter. And the filter actually extracts the vessels where the bubbles are too numerous to be distinguished from each other. So for the heart itself, it will be difficult, but for the myocardium, that will be possible. But it moves a lot, so you have to correct. And if you have to correct in the 3 dimensions. If you have to correct in the 3 dimensions, you need a 2D matrix doing plane wave imaging. If you do a 2D matrix doing plane wave imaging, you need thousands of channels. And so you need a lot of money. And so currently we're limited with the amount of material that we can use for that.
Well, thank you, Olivier, again.